Next thing we have to cover are Riemann sums. There are 4 kinds of Riemann sums. There's left, right, mid, and trapezoidal. What is a Riemann sum? Oh my god, that's such a good question. So if we have a function and it looks like this, and we're trying to find the area under the curve, how would we do that, right? Especially if I say go from 1 to 5, find the area under this curve. What could you do? Well, before we were making shapes, right? So you can make a rectangle here, and then maybe like some kind of triangle, and then something up here, right? But it's just like that's kind of hard, bro. And this like swoop here is just, it's not a shape that you can just make and calculate easily. So what a Riemann sum is, we'll start with a left Riemann sum. You draw rectangles with the top left corner touching your function, touching your line. So if we split this up into 4 rectangles from 1 to 5, and we make sure all the left corners are touching our function, we could calculate the area of each of these rectangles and get a rough estimate. So for this one, for example, this has a width of 1 and a height of 1, so the area is 1. This has a width of 1 and a height of 2, so the area is 2. This has a width of 1 and a height of 3, so the area is 3. And our last rectangle here has a height of about 4.5, so we'll call it 4.5. And now if we add all of these areas together like we were doing before, we get 10.5 units squared. And if you notice, there's all these blank spaces that aren't covered by these rectangles. So that means that our estimate of 10.5 is going to be an underestimate because there's all this blank space that we're not accounting for. If we look at this same function and find what's called a right Riemann sum, we'll do the exact same thing, but now the top right corners of our rectangles are going to touch the function. So we'll draw a rectangle here, and we'll use the same width as before. So we have our right Riemann rectangles here, and we can add up the area of all of these. This width is still 1, the height is 2, the width is 1, the height is 3, the width is 1, the height is 4, and the width is 1, and the height is 5. If you add all of these up, you'll get 14 square units. And this one's bigger than the last one, right? Because we have all of this area that's over our line that we are counting now. So if you use a right Riemann sum on a function that's concave up, you're going to get an overestimate. So this is an overestimate. These are 2 basic kinds of Riemann sum. They're the ones you're introduced to. So what's important to know is that if you have a function that is increasing and you use a left Riemann sum, it's going to be an underestimate because your rectangles are going to have all this empty space that you're not counting in your area of your rectangles. And if you use a right Riemann sum on a function that's increasing, it's going to be an overestimate because you have all this extra space that you're counting that's in your rectangles but not a part of your function. That's not under the line of your function. The opposite is true when you have a function that's decreasing, because if you use a left Riemann sum now, your rectangles are going over your function and you have this extra space. And if you do right Riemann sum rectangles, right, they're going to be underneath the line, and there's going to be empty space above all of your rectangles. So go ahead, try this, practice it right now. So let's do it. The question says approximate the area between the x-axis and g of x equals 2 to the power of x, from x equals -2 to x equals 2 using a right Riemann sum with 4 equal subdivisions. This was just a practice problem I got off of Khan Academy. So it says to make 4 divisions in between -2 and 2 and to find the area using a right Riemann sum. So our first step is, it says 4 equal subdivisions, so we have to find out how big each subdivision should be. In this case, it's easy because our range is 4 long, so we're going to use each subdivision is going to be 1 unit long. This is just the function it's giving us. It's this curve right here. And yeah, right Riemann sum means that you take the right corners of the rectangle and you put them on the line. So let's start with 2. We'll go up. We'll put the right corner on it, and we'll draw this rectangle. And then we'll go up at 1, and we'll put the right corner on the line and go to 0. We'll go up from 0. We'll put the right corner on the line, and we'll go to 1. And we'll go up from 1, put the right corner on the line, and go to 2. So now that we have our rectangles drawn, all we have to do is calculate the area of each. In this case, it's easy because the width of each of them is 1. So our first rectangle over here has a width of 1 and a height of 1/2. So the area is going to be 0.5. This one has a width of 1 and a height of 1. The area is going to be 1. This one has a width of 1 and a height of about 2. So we'll say it's 2. And this one has a width of 1 and a height of 4. We add these all up, we'll get 7.5 units squared. Now, is this estimate an overestimate or underestimate? What do y'all think? Write it down. Okay, look, we have this extra space here, we have this extra space here, we have this extra space here, and this extra space here. That is not a part of the actual area, but we are counting it, so this is going to be an overestimate. So we have all this extra that we're counting. So the answer that we're going to get is 7.5 units squared, and this is an overestimate. estimate. The last thing we have to know about left and right Riemann sums is how to calculate them from a table. So in this case, we have a table here of a function that is increasing. So let's say we're trying to find our left Riemann sum and our right Riemann sum. So how would we do that? If you visualize this graph, we're gonna have a point at 4, 5, 8, 10, and 16, right? This does not have to be perfect. It's just a random graph to just help visualize it. So you have this graph, it's increasing, and you're gonna have our left Riemann sum, so we're making left rectangles, right? So if we draw our first rectangle from 3 to -1, what is the width gonna be? It's gonna be the distance in between these two numbers, right? Because it's how long the bottom of the rectangle is. So the distance from -3 to -1 is 2. And then what's the height gonna be? It's gonna be whatever this y value is, which is 4. So this is gonna be a 2x4 rectangle with an area of 8. Now for -1, what's the distance between -1 and 0? It's 1. And what's the y value? It's 5. So this is gonna have an area of 5 because it's a 5x1. Now if you see the pattern here, you don't actually need to draw the graph, and you just look at the table, right? Because the bottom of the rectangle, the length that it's gonna be, is your distance in between these two numbers. So our rectangle from 0 to 2 is gonna have a width of 2 and a height of 8 right here. Because you're using the y value from the left one, because the left corner is what's touching the line. So this is gonna be 8. And for our last rectangle from 2 to 5, it has a width of 3, because it's traveling 3 to get to 5, and a height of 10, because it is the y value of our left point. So the area is going to be 30. That's going to be it for this, because we don't have to draw a rectangle for, we don't have to draw a rectangle at 5, because there's no point for it to connect to over here. So when you're doing a left Riemann sum and you're using a table, you can ignore the last y value, because you're not ever going to draw a rectangle using it. So if we add up our totals, we're going to get 8 plus 8 plus 5 plus 30, which is 51 units squared. Now the right Riemann sum, let's try it without drawing the graph, because we found the pattern, right? We just use the pattern. I like to do it when I'm doing right Riemann sum. I look at the table from right to left and I draw rectangles this way. A lot of people that I've told that to say that that's really weird. So if you want to, you could go from the left to the right and just ignore this value here. But I think it's easier if you just go from right to left and you create the rectangles from right to left and then just ignore the last one. So if we start our first rectangle, the width is going to be 3 times, the height is going to be 16 because you're using the right one. So 3 times 16 plus, and then your second rectangle, the width is going to be 2 because it's from 2 to 0. Your height is going to be 10. Your third rectangle is going to go from 0 to -1. So the width is 1 and the height is 8. And your last rectangle, you're going from -1 to -3. So the width is 2 and the height is going to be 5. So then if you just simplify this, you have 48 plus 20 plus 8 plus 10. You're going to end up with a value of 86. And these are so different because our left one is an underestimate and our right one is an overestimate. Also, side note, this is kind of unrelated, but the more rectangles and the smaller rectangles you have, the more accurate your estimate is going to be. Because let's say we try to do this with 2 rectangles. We have one here and one here. There's this huge empty space here and this huge empty space here, right? But if we did this with like 5 rectangles, we had one here, one here, one here, one here, one here, we only have this little tiny empty space here. Same is true with the right Riemann sum. It's just you have less overestimates. But the more rectangles you have, the more accurate it's going to be. And in this one, we're covering a distance of 8, and we're only using 4 rectangles. So both estimates are going to be not very accurate. So you should just keep that in mind. So I have another Khan Academy problem. Go ahead, pause it, try it yourself. Use the table. I'll even make the table bigger for you. I'll go ahead, try it, solve it. All right, cool, my turn. So left Riemann sum. You're drawing rectangles from left to right because you're using the left Riemann sum. So first you can look at is the distance between the two, which is 3, times the y value of your left point, which is 2, plus distance between the next two is 1, times your y value is 5, plus the distance between your next two, which is 4, times your y value, which is 7. And then you simplify this out, you get 6 plus 5 plus 28. The next thing we're going to look at are called midpoint Riemann sums. They are a lot less common. You don't really use them that often. But if we have a function that is growing like this, and we want to find our midpoint Riemann sum, what you're going to do, you're not going to believe it, is you put the middle of the top of the rectangle on the function. So before, we were doing either the left corner or the right corner of a rectangle. We're touching the function, right? But for the midpoint, you want the direct middle to be touching the function. So to do that, normally what you would do is we have a point here at 1, we have a point here at 3. You want to pick the point 2 in the middle, and you'll find where it touches the line at 2. So we'll draw our midpoint rectangle like this. And then from 3 to 5, you're going to want to find where 4 touches it, and you put your rectangle like this. And for 5 to 7, you're going to see where 6 touches it, and you'll put your point right here, and the middle of your rectangle will be touching the function. So if you look, this has a little bit of overestimate and a little bit of underestimate, so that kind of tends to balance out a little bit. So the midpoints are going to be a little bit more accurate. And just for fun, let's add one rectangle from 7 to 9, and we'll go where 8 is touching our function. So if we were trying to find the area under the curve from 1 to 9 using a midpoint Riemann sum, we would use rectangles like this and then calculate the area. So our first one, the width of this rectangle is 2, the height is about 1.5, so the area is going to be 3. This next one, the width is 2, the height is about 2, so the area is going to be 4. Next one, the width is 2, the height is about 3, so the area is going to be 6. And our last one, the width is still 2, the height is about 5, so the area will be 10. Now we add these up as usual, we'll get 23 units squared. You rarely have to find midpoint Riemann sums on graphs. You normally use it with tables, so we'll look at that next. So I got another problem up. I don't know if you could tell, but I made this myself. So go ahead and estimate the area of the function using a midpoint Riemann sum on the interval 0 to 6. This should be a comma. That's on me. 0 to 6 using 3 subdivisions. Go ahead, try this yourself. Try to figure it out using the same logic that we did for left and right Riemann sums. All right, man, I'll go over it now. So our midpoint Riemann sum, we're going to want to make rectangles that touch our function in the middle of them, right? So if you look 0 and 2, what's in the middle of 0 and 2? We have 1, right? So you want our rectangle to touch the function at 4 because it's in the middle of 0 and 2. So 3 subdivisions mean we'll divide it here, here, and here. We have like 3 different rectangles. So this first one, the distance from 0 to 2, how long is that going to be? That's going to be 2. And what's the height is going to be whatever it is in the middle, which is 4. So we'll have a 2 by 4 rectangle plus our next one. Our distance from 2 to 4 is also 2. So we'll have a 2 by 9 rectangle because we're looking right here. And our last rectangle, the width is 2. The height is going to be 12 right here. So we'll have a 2 by 12 rectangle. So we multiply this out. We get 8 plus 18 plus 24. Add that up and you'll end up with 50 square units. The last type of Riemann sum that we have to look at is called a trapezoidal Riemann sum. So, as the name suggests, we're going to be making some trapezoids. So, on this function here, you have all these curves, right? If we make left endpoint rectangles and we use a bunch of subdivisions, we're going to get crazy overestimates, crazy underestimates. It's going to be like off. We have this underestimate, overestimate, underestimate, right? You're going to get a really inaccurate graph. Same thing with right Riemann sums, because you're going to have all this overestimate, all these underestimates, whatever. Trapezoidal Riemann sums are the most complicated, to be fair, but they are the most accurate. So the way that trapezoidal Riemann sums work is you're going to draw trapezoids. So for example, if I connect the right corner and the left corner both to the function, and then I connect them here in between, what we have is a trapezoid, and we have a pretty close estimate of what our function is going to be, right? Same thing if I go from 2 to 3 and I connect the corner up here, I draw a trapezoid like this. Obviously, it's not perfect. We have this little area here, but it's way closer than if we drew a right or left Riemann sum. Same thing with -2 to -1 and -1 to 0. So we can draw these trapezoids on every point, and instead of making rectangles, make trapezoids, and we'll get a way more accurate estimate of what the area under the curve is. So in this case, we split it up into 6 trapezoids of equal length, equal distance apart, right? So how would we calculate this area? Formula for the area of a trapezoid is base 1 plus base 2 divided by 2 times the height. This you should know from geometry, but in case you don't, write it down now, remember it now. So to visualize that, if you draw a trapezoid, I'm gonna draw it sideways because I like them more sideways. Our base 1 is a little bit slanted, but ignore it. Our base 1 is this down here. Our base 2 is this up here, and our height is, you know, the height. So on our trapezoids, it's just this, but like this way, right? So our base 1 is this length. Our base 2 is this length, and our height is the distance between the two, right? So if you look at our first trapezoid right here, our base 1 is this side right here, which is going to be our y value at -4, which is 2. And our base 2 is this y value at -3, which is like almost 6. I'll go like 5.8, right? And then follow the formula over 2 times h, which is the height, which is the distance between the two, which is 1. And our next trapezoid, we have, again, 5.8 is the same y value, plus the second y value of 6 over 2, and then again times 1, so I'm not going to write that, plus 6 plus base 2 is like 4.5 over 2, again, times 1. And then our next trapezoid down here is like 4.5 is the first base. Second base is like 3 over 2 plus, again, it's like 3 plus 2.5 over 2 plus our last trapezoid is 2.5. And the second base is up here at around 5 over 2. And if you add all of this up, I'll save you a bit of time. You'll get 50.6 over 2 or 25.3. And this is going to be square units. So we'll look at another graph, one more example. We'll go step by step, and then we'll look at a table. And that will be it for Riemann sums. I have another Khan Academy graph up. Let's try solving it and try using a trapezoidal sum with 3 subdivisions. So it says we're going from 2 to 5 using 3 divisions. So 1, 2, 3, you know, makes sense. Go ahead, pause it now, try it yourself. All right, cool, let's go. So first we have to draw our trapezoids. So connect it at the y values and boom. And then again at the y values and boom. Then again at the y values and boom. Now we'll find the area of each. In this case here, it's helpful to look at the actual equation because it's hard to estimate values on this graph, right? So we know that if it's 1 over 7 minus x, we know that at 2 it's going to be 1 over 5, right, which is 0.2, which makes sense right there. At 3, it's going to be 1 over 4, which is 0.25, right? So your base 1 is 0.2. Your base 2 is 0.25. Again, over 2, and then times 1. So this is going to be your area of your first trapezoid. And if we look at our second one, we already know that our y value at 3 is 0.25 plus 1 over 7 minus 4 is the same as 1 over 3, which is 0.33 over 2, again, times 1. And our last trapezoid here, if we plug in 4, we already know is 0.33. And then 1 over 7 minus 5 is just 1 over 2, which is 0.5. And again, this is over 2 times 1. If you add all of that up, you get 1.86 over 2 or 0.93 units squared. And this is your trapezoidal area. And we'll look at a table real quick. Okay, so now we have to find trapezoidal Riemann sums from a table. This problem, again from Khan Academy, the GOAT, says approximate the area between the x-axis and f of x from 0 to 9 using trapezoidal Riemann sums with 3 equal subdivisions. That's 3 subdivisions. That's easy. 1, 2, 3, right? So if we're trying to make trapezoids out of these, like this, and we're looking for base 1 plus base 2 over 2 times the height, our base 1 is going to be this, which is going to be our first y value, which is going to be 2, and then plus 5 over 2, and then times the height, which is the distance between the two numbers, which is going to be 3. Plus, same thing for the next one, 5 plus 7 over 2 times 3. Plus, same thing for the last, 7 plus 11 over 2 times 3. This is a lot easier if we multiply the 3 at the end. So we can rewrite this whole thing as 3 times 2 plus 5 over 2 plus 5 plus 7 over 2 plus 7 plus 11 over 2. We could combine all these fractions. Nothing's really going to change. We're still going to have to do a bunch of addition. So we get 7 over 2 plus 12 over 2 plus 18 over 2 all times 3. If we add this up, we get 37 over 2 times 3. And if we multiply this 3 and this 37, we end up with 111 over 2 units squared. This is as simple as it goes because 111 is not divisible by 2. If you really wanted to, you could say 55 and 1 over 2, but that's kind of dumb. So this is it. Anytime they just give you an equation and they don't give you a table, like if this table was not here, but instead of saying f of x, set an equation, what we could have done is just made this table and solved it. So anytime they just give you an equation, go ahead and make a table. It makes it easier. Or if you really wanted to, draw it, but I think that's harder. Yeah, so that's it for Riemann sums. Now we get to move on to calculus. Oh my goodness.